Welcome, Justin. It's going to tell us about some really cool both functionality in the Enclave for sharing um, analyses and code, but also a cool application of it for ontologies. Oh, we have one new loginer. Hey, Suzanne.
Hi there.
Justin's just about to start.
Oh, good.
You guys see my screen?
Mhm.
Okay, so let's keep this very informal. If something doesn't make sense, just interrupt me. I'm not sure you typically take the whole hour, but something tells me I might not take the whole hour.
That's
but,
okay. We
that
are
Q&A.
actually totally
Okay.
short.
So I'll tell you about tools that we've developed to do semantic similarity and clustering in N3C. This is me talking, but actually this is the result of several years of blood, sweat, and tears from the coffee hackathon group. And so it's not just me. And anyway, I think the things that we provided and the one I'm going to talk about today are basically three tools that I think are appropriate for reusing. They're ready to be reused. And so we will walk you through what we've used this for, but I think that others are unlikely to use it for exactly what we used it for. But you can, as you're listening to this explanation, it may occur to you sort of the ways in which you can use these three Lego pieces that we made to do what you want to do in the Enclave. And the three tools are extracting HPO terms from OMOP data. There's a couple ways of doing that, and the one that I'll walk through today is only one of the three ways that I know about to do that. But we have working code. I should say also we have working code for all of these, and I will walk you through it at the end here after I'm finished talking. So extracting HPO terms from OMOT data, that's the first thing. Second thing is probably the star of the show, which is calculating semantic similarity from those HPO terms. So you can have HPO terms for two patients and compare them, and you basically get a floating point number that says how similar all of their phenotypic features are. Or as Brian's used it for, here's a patient and here's a disease. How well does this patient match the disease for a protein profile? So conceptually, patients and diseases are the same thing in this universe because they're just a set of HPO terms. And so we have tooling to do that. I'll go into that in a minute. And then what we use this for our long COVID clustering work was here's a bunch of patients, compare them to each other, and then you conceptually you get a giant n by n matrix of like how similar every patient is to every other patient. And you can plug that in. There's lots of things you can do with that, obviously, but we plug that into k-means clustering and use that to define subtypes of long COVID, and I'll walk you through that in a minute. So, like I said, our use case here was to cluster long COVID patients. This is what I was saying before, is there's actually at least three sources of HPO terms for patients in the Enclave that I know about. The first one, the one we'll use in this example of the code that I'll show you later, is OMOP to OBO. This is Tiffany Callahan's awesome work, basically well, she can tell you a lot more about it than I can, but what we use it for basically is to extract HPO terms from the condition occurrence table. There's also this stack called lunk to HPO, which is what it sounds like. It's basically lab measurements to HPO terms. We use these two in the clustering paper. The code I'll show you will only use this. And this is a source that we haven't made a lot of use for, but we sort of done some data diving, is clinical notes from Hong Fan's work actually provides quite a few HPO terms, and that's just throwing that out there. I'm probably not an expert in how to use it, but that does exist, and you can directly just get HPO terms from clinical notes. I think there's like a notes and a notes NLP table alongside the OMOP tables where that lives. Okay, so for all the patients, we extract their HPO terms, and then we compare the patients using this algorithm called the phenomizer, this semantic similarity calculation that I was talking about before, and then make clusters. So I'll show you how to do this first thing in the code, but probably we don't need to dwell on
Justin,
too much because basically it's just, yep.
Two questions actually. One is, when you say LOINC to HPO, I'm not very familiar with LOINC or HPO or OBO. Is that just like the lab tests or the measurement values as well?
It's the lab tests and the results, and then so what happens is somebody gets a test, right? And like, here's their blood glucose level. And then it's like 150, and then there's predefined reference ranges, right? So if it's above 100, then you have hyperglycemia. And so what LOINC to HPO does is say, give me the value, you compare it to the reference. Is that high, normal, or low? And then if it's high, then you are annotated with the HPO term for hyperglycemia. If it's low, you're annotated with hypoglycemia, and if it's normal, then you're not annotated with an HPO term. Does that make any sense?
Yeah. And then can you just describe HPO a little bit? I'm vaguely familiar, and I imagine others might not be.
Oh yeah. So HPO is an ontology, human phenotype ontology. It was originally so this is Peter Robinson's work. It was originally made to define ontologically all, like, basically everything that can go wrong with the human body in the context of rare disease. In practice, this is used for basically all disease, depending. I mean, this is kind of the best way to ontologize, if that's a word, human phenotypes, like basically symptoms and signs from diseases. So it's if you're not familiar with that, ontologies basically it's just a hierarchy of everything can go wrong with the body. So up the top you have phenotypic abnormality, and then you have, like, abnormalities lungs, and then under there somewhere is cough, and without going into big long thing, this is a directed acyclic graph. So some phenotypes can be children of different system abnormalities. Like, I can't think of an example. Maybe Hannah is an example. Like there's heart abnormalities. It can also be lung abnormalities, or I don't know. Anyway, that's kind of the long and the short of it.
Cool.
Yep. Okay.
I'll
So
just throw in one. Sorry, excuse me. Just one comment. Just to emphasize that the HPO, the HPO is about phenotypic abnormalities. So it's not designed to describe healthy people. It's designed to describe disease symptoms. So as Justin was saying before, if you have a blood sugar test and the result is normal, there's no term in HPO for normal blood sugar. There's a term in HPO for high blood sugar. There's a term in HPO for low blood sugar, but there's no term in HPO for normal blood sugar.
Yep, that's kind of an important point when you get down into the nitty gritty of modeling the data you have. But, for here, in the context here, we're not dealing with anything. It's normal. So these are all abnormal things from the HR data that are translated to HPO terms. Okay, so how do you do patient-patient semantic similarity? This isn't just how you do it here. This is just conceptually how you would do it. Here's a patient 1, here's patient 2. We have some signs and symptoms, respiratory finding, acute kidney injury, chilblains. So the idea here is to do something more sophisticated than sort of exact matching. Chilblains here is chilblains there, and then to ignore all these fuzzy matches. So basically, it gives you a way of doing fuzzy matching, among other things, gives you a way of doing fuzzy matching between, like, say, respiratory finding and cough. So maybe conceptually you give this a 1, and this would be some fraction of a 1 as far as similarity. That doesn't actually work that way from 0 to 1, but get the idea. So how do you do that? Basically, we take those OMOP terms, or terms from the condition occurrence table. These can also be from the measurement table if we're using length HPO. You're basically translating those codes onto this DAG that we talked about before, which is the human phenotype ontology. And so here's acute kidney injury, here's transient renal failure, which is mapped to the HPO term reversible renal failure. So those are 2 terms, and what we do is we walk up the DAG until we find their common ancestor and find the information content of that common ancestor. If you're not familiar with information content, this is basically a measure of how meaningful that match is, or conversely, how surprising that match would be if you found that by random chance. This basically just requires some measure of term frequency, and so hopefully that makes a bit of sense. So the idea is, if two terms are very dissimilar, that you'll have to walk the whole way up to the top here, and the information content will basically be 0, because every kind of abnormality is a phenotypic abnormality up top. Conversely, if they meet down at the bottom, or if they're the exact same term way down in the bottom in the leaf, then the information contents can be very high. Okay, so we spent quite a bit of time implementing this as a Python library. The algorithm I just described, well, I may actually slip up and call it the phenomizer, but that's what I mean when I say phenomizer, is how similar is patient 1 to patient 2. Oh, sorry, let me go into a bit more detail about how this works. So basically, you take patient 1, you find the best match for chilblains over here, which is chilblains. You find the best match for chronic kidney disease, which is maybe nephropathy. Best match for abnormality of the respiratory system is cough, and you average all of those information content. So that's for patient A. That's the sort of average similarity of the best matching term from patient A to patient B. And then you do the opposite. You start with patient B and find the best match for cough over here. Nephropathy also is chronic kidney disease is the best match. You can see that this is not, it's different going from patient A to patient B versus patient B to patient A. So you get a slightly different, or maybe wildly different measurement here. And so you have a measure of patient A to patient B, you have a measure of patient B to patient A, and then you just average those two. And that is, we'll sometimes call that the phenomizer score, but that is the measure of semantic similarity of all the signs and symptoms that we know about from patient A to patient B.
Justin?
Yep.
That sounds like a weighted bipartite matching kind of thing. Am I on the right track, or is this something totally different?
Yeah, I think that is a good way of describing it. So this is kind of a bipartite comparison.
So do you have to compute, like, for every patient A symptom, the similarity to every patient B symptom?
Not everyone, just the best matching one.
I see.
And it's not weighted, it's weighted within for each patient, but actually patient A has the same weight as patient B. You're weighting both directions equally. So, but they are weighted with respect to, like, within one patient, if that makes any sense. So in other words, if you had like 1,000 HPO terms for patient A, it would be the average similarity of the best match from patient A from each of those 1,000 to the best match in patient B.
Thanks.
Yep. Okay, so we spent some time implementing this in the enclave, and we wrote this. This was our intention from the word go, was to implement this in a way where it can be shared across all DURs and reused. And so it warms our heart when people use our code. So this is shared as, sorry, excuse me, a Python library called semantic similarity with no spaces. So, well, I'll show you that later, where that shows up if you're using a code repo, but basically just type in semantic similarity and it should come up as a library and you can just use it. So that's the patient similarity. I forgot, I was going to make a sort of an all by all patient grid so you could see what that looks like. But anyway, so we now know for this use case, if we have 1,000 patients, say, or I think for the long COVID clustering paper, we used 2,256 patients. We just make a giant matrix, which is 2,256 by 2,256. So you know how similar every possible pair of patients is. We can feed that to another library we wrote called kernel KM, which is our implementation of k-means clustering. And so without going into a big long thing, basically the idea here is we sort of define this space, which is how similar every pair of patients is, and so we pick at random if we're looking for 6 clusters, we pick sort of 6 random places in latent space and just group the patients by whatever cluster they're closest to, whatever point, whichever of those 6 points is they're closest to. And then that's kind of defines a group of patients, each cluster, and then you average that group of patients and you get sort of a new centroid. That's what they're called, centroids. And then you regroup patients because patients may have moved closer or farther away to each of those 6 clusters. And you do that iteratively until you stop improving the clustering. Probably, if that doesn't make any sense, you can just Google k-means clustering. That's was my attempt at explaining it. But anyway, so this is implemented as a Python library also in the same way as before. If you just type kernel KM, it will come up and you can just choose it and then use it in your Python code. Just by the way, here's what we came up with. I won't go into this too much, but in this same package, k-means clustering, we also wrote quite a bit of helper code. And one of the things that you can do if you have a group of patients and you've clustered them into, say, 6 clusters, you can actually use the HPO terms themselves to define the clusters. And what I mean by that is, say we were talking about hyperglycemia before. If hyperglycemia tends to occur in certain clusters and not in other clusters, there's a very simple statistical test you can do called the chi-squared test to determine that. It won't off the shelf tell you which clusters it's higher or lower in. You kind of have to figure that out yourself with an ad hoc or a post hoc statistical analysis. But that is also implemented in the kernel k-means package, and I don't think I have code to show how to do that, but I could write some fairly easily. So, for example, I think we found 116 HPO terms that we were actually able to extract from the condition occurrence and measurement table that are sort of symptomatic of long COVID. Among those, these were significant by a chi-squared test. And then we did some post-hoc analysis. I should say Elena Kasaragi did a post-hoc analysis to say which one is higher and lower, but we sort of color-coded those here. So, for example, nasal congestion was much higher in cluster 4, which makes sense because that's sort of the, I think that was a pulmonary cluster, is that right? So, I'm trying to think some other things. Lymphopenia is a lab test. This is coming from Loink to HPO. That is very high in cluster 1, which is that makes sense because cluster 1 is defined by one of the things that's defined by is abnormal lab values. Anyway, I won't go into a big long thing, but all that to say that in addition to using HPO terms to actually cluster the data, you can actually you can characterize the clusters themselves without a whole lot of extra work because you have the HPO terms for all of the members of each cluster. And so you can do some pretty simple statistics to actually characterize the clusters after you've made them. That makes sense? Okay, so I spent a bit of time this week pulling out the code that we wrote to do everything that I just described. And so I made some notional code. I don't think I'm allowed to, or but I probably shouldn't show you the code that we used in the DUR, in the long COVID DUR. But I can show you this code because I sort of copy pasted it and implemented it in what's that called, the playground? Anyway, it's someplace that doesn't have real data.
Area.
That's it, training area. So like I said before, there's kind of 3 steps here, and so and 3 sort of Lego pieces that you can plug into your own analysis. And so I made a code repository for each of those. I won't go up on a soapbox too much, but code repositories, I think, are just a far superior way of developing code in the enclave. They have a lot of features that make development a lot easier than, for example, in code workbooks or contour analyses or anything like that. Anyway, if you haven't looked at code repositories, you should, because they're, in my opinion, it's just the best way to develop code in the enclave. Anyway, so here
Justin, can I interrupt you for a moment? Can you only use code repository if you code in Python?
No, you can do code in SQL, Python, Java, I think, but I've never done it.
But not R.
Not R. That is an important point, is that if you need to use R, which a lot of people need to do, like there's some statistical packages that basically the community always uses R for them, and in that case you have to use a code workbook. Also, I should say visualization, you have to do in a code workbook too. So at some point, if you use these things to do anything complicated, you're going to have to go to code workbooks. It's very likely. Yeah, so these basically are my intention anyway, is to just break off those Lego pieces. And if people want to reuse the code, you could probably just look at this, at these 3 code repositories and just copy paste them or fork the code and use them, hack them up and use them to do what you want to do. But I thought it might be useful to actually walk you through the code. And the 3 steps here are extracting HPO terms. Like I said, this is, should have written just the OMOP to OBO part of that. There are other ways of getting HPO terms, but here we'll just be using OMOP to OBO. This is an SQL transform. So like I said, as far as I know, for code repositories, you can use Python, R, and not R, Python, SQL, and Java. What's that?
I was just going to say Java, yes, but not R.
Not R.
As we were saying before. Yeah.
Yep. There has been talk of, I think we sort of been politely nudging Palantir to maybe think about implementing it. And then there was also blank on the name, Andrew Williams had somebody talk at one meeting maybe a year ago, talking about maybe making RStudio available somewhere.
These are persistent rumors, but to date there has been no substantial change in this situation.
Yeah, I think it's unlikely to be the case that you'll be able to use R anywhere other than a code workbook in the near future is my understanding. Okay, so here we're extracting HPO terms for patients. There's no reason at all that you have to do this in SQL. You could do it in Python, you could do it in Java, you could do it in R, but I'll break it down. I won't go into gory details about how this might work, but I'm using notional data here. This is Cynthia data, so it's fake data. We're just joining the person table to the condition occurrence table on person ID. That's just dead simple SQL. So this basically just gets all the condition occurrences for each patient. Here we're going and getting this code actually won't work, I don't think, in the playground or whatever that's called, because I don't think in the playground you can see this file. But this is a very simple join of two tables that Tiffany Callahan provided. I think so. This is OMOP to OVO version 1. In version 2, you don't have to do this inner join, but we are still using version 1. Version 2, you get a lot of new goodies, and Tiffany probably can tell you in great detail about what the difference is. But version 1 works pretty well for our use case, and but version 2 does exist if for some reason you want to check that out. Anyway, this will basically get you the mappings from the condition occurrence table to HPO terms. These are the actual mappings. And then this is some fairly ornate code to actually for each patient. Transform 1, we got all of the conditions for all the patients, and now we're just translating them to HPO terms if there's a mapping. Like I said, this is notional code. It's likely that you'll have to play around with it, or hack it up if you want to do something in your project. Okay, so now we have the HPO terms. Here is how at least one way to do the patient-patient similarity matrix. So ultimately, that's kind of what we want from this, right? Here's a bunch of patients with their HPO terms. That's the input, and the output is this all-by-all similarity matrix that we talked about before. There's basically 2 steps to that. The first is you need the actual HPO graph. This version of the HPO graph is getting a little long in the tooth. It's kind of old, but it does actually work. I think it's from about 2 years ago. And so if you need HPO terms that have been minted in the last 2 years, this is probably not the way to do this. I don't know of any other source for HPO at the moment, though. So basically, this just gets you the graph, and then this is the entirety of the code to do this. Basically, you make this phenomizer object. Like I said, phenomizer is just what we call this algorithm. You make what's called a Mika D. I told you before that to figure out what the information content is between for any node in the graph, you need to you need counts basically, and so this counts in for you. So you give it your actual data, and it will count the number of times like lung abnormality or any of its children occur in your data. So this is kind of the frequency in your data for all of the HPO terms. And then you just make a call to make patient similarity matrix. That's not what it's called, but that's basically what it's doing. And this is your all-by-all matrix. And then this is just some helper code that I wrote to turn this from a long data frame into this all-by-all matrix that we talked about. Okay, so we have HPO terms. We have the patient-patient similarity matrix. Where'd that go? How do you do k-means clustering? This is also a Python code repository. There's only one transform here, and this basically is the entirety of the code. This, by the way, is this does not use Spark data frames, so it probably will not go fast or even work if you have like 1 million patients. It's possible to do machine learning on large data sets like that, but not probably with this library. There's a package called PySpark ML that can handle large swaths of data. I don't think they have a k-means implementation. Yes, they probably do. I don't think you can feed a patient similarity matrix to it, which is why we implemented this.
I was going to ask actually if there was, I know it'd be a completely different method, but there is a k-means, but they want feature vectors. And so I wonder if there's a sort of ontology-based embedding that could be generated.
Yeah, that actually would be, I don't want to say easy, but one way to do that actually would be to just embed the entirety of the monarch graph, which contains HPO, and then you get embeddings for all the HPO terms, and you could generate feature vectors that way. What that does not take into account the frequency of each HPO term, and so that you would lose some of that magic. I mean, depending on what you're using it for, that might work really well or it might not work at all.
I suppose it depends on how you would, because you'd get a bunch of HPO term embeddings and then they need to be sort of combined to make a patient embedding, right?
Yeah, we've talked a lot in our group about how to do that. There's no one right way of doing that, but you could average them. Another thing we've talked about is you can imagine that's not quite right though, because I mean it depends what you're doing, but like that might be drowned out by like things that aren't quite important for your use case. If you have like 100 abnormal lab values, but like the thing you're really interested in is some like cardiovascular issue or something, then obviously the 100 lab values are going to drown out that signal. That may be what you're really interested in. So another way of doing it, which we haven't actually done this, but it wouldn't be rocket science, is to just break out the disease into like say 6 organ systems and then do an average embedding for each organ system and then average those, because it would prevent that problem I just said. Or you could just ignore the organ systems you're not interested in. Anyway, this, like I said, this works. It scales to at least thousands of patients. If you have 100,000 or more, it's almost surely not going to work. But there are machine learning methods that work in the enclave using PySpark that can scale that well. Excuse me. So let me read my own code here. This is actually generating the data for an elbow plot. If you're not familiar, basically elbow plot is one way of deciding what your K should be. It may sound like kind of begging the question in a logical sense to ask how many clusters there are of a thing, and then you actually have to tell the algorithm how many clusters you want. But that's kind of the way it works depending on the algorithm you use. And so the idea here is you just investigate a whole bunch of different Ks, different number of clusters from like 0 to 20. And you look at the curve of the error, like how well patients fit into their cluster. And then it in some cases falls off really rapidly, and then it sort of levels out. And so the idea is just to pick the elbow, like where it levels out. And that's what this does. There are, I should say, more sophisticated ways of picking K, and this is kind of the old school, but nobody really thinks that's the best way of doing it. It's okay though. I don't have code for this here, but somewhere in here there are those chi-squared implementations that you can use. So if you want, like we talked about before, once you make the clusters, if you want to characterize them, then there's code in there to do just that. And I think that is a wrap. But like I said, this is notional code, but without too much effort. If you have any interest in using any of these 3 Lego pieces, it shouldn't be too hard to use them, and it warms our heart when people reuse our code and our data. And so if it's of interest, then you're very welcome to coffee hackathons to come join us, and we can help you, or just ping us asynchronously, and we can help you get it working.
That's very cool. I will note that for those who do prefer code workbooks, I believe the Python library works in that environment too.
Should do. Yeah.
So how complete, I know you sort of take the condition and then you map them to HPO terms. Do you have any sense of how many conditions end up getting a mapping if you sort of just take a slice of data?
That's a good question. I can give you one data point, which is for the way we did the long COVID experiment was there's a Rachel Deere had this paper that defined 287 signs and symptoms of long COVID. And then when we went to try and map those, we were able to extract successfully and actually pull HPO terms from actual patients for 116 of those. And so if you want just a ballpark, like by that metric, you're going to get about half, maybe less of any set of conditions that you're interested in. Oh, sorry, that is using OMOP to OBO and LOIN to HPO. So I think if you use those, if the experiment I said is valid, then you would probably get about half of the ones you're interested in if you use both of those stacks to get HPO terms.
Justin, is LOIN to HPO, is that's still being worked on?
Yeah, that's from Peter Robinson's lab.
Yeah.
Mike Gargano, I think, is heading that project. He's developed a lot of the code that we have used to extract HPO terms, and I think he's actively still working on it.
Okay.
It is it's challenging because basically somebody has to, I mean, there are reference values for all of the measurements basically, because that's what doctors use to figure out if somebody is abnormal or whatever. But it's a pretty deliberate process to actually use those and link to HPO, and basically kind of have to curate them, or just put them in place semi-manually.
Awesome. Well, thank you so much, Justin.
My pleasure.
Yes, thank you.
Yeah. All right. Well, we'll hang it up here. And there's so many ideas that there's like 1,000 different ways to slice all these cool data. Unfortunately, ideas are cheap and work is expensive. All right. Thank you so much. We'll get the recording posted up. I'm going to actually do this one and our last one, I hope, today. So
Thanks, Sean. Have a good weekend, everyone.
bye all.
Bye, everyone.
Yep.